So let me explain this phenomena through a figure because these 3 points are very important if you want to fully understand the working of a support vector machine. Okay, let's have a look at this figure. I will explain these last 3 points again. Now in this figure, you can see that on this left hand side, we have two different sets of data, right? We have one set of data here, right, and we have one set of data here. So these are two sets of data, and these two sets of data belongs to two different classes. So we have different objects here, we have different objects here. These objects belongs to, let's suppose, class A, and these objects belongs to, let's suppose, class B. So we have two different sets of data belonging to two different classes. Now I want to have a decision boundary or a hyperplane which could successfully separate these two classes. So I know that this is my decision boundary or hyperplane in 2 dimensions. So I can draw a hyperplane which is shown here as L1 in this direction. So this L1 can classify these two different sets of data into different categories, right? Now I can also have another hyperplane which I can draw in this direction, which is named as L2 here, and this L2 or second hyperplane is also able to classify these two training data sets correctly, right? Now there is also a possibility that I can have another decision boundary or hyperplane which is named here as L3, and I can draw it in this direction, and this decision boundary L3 is also successfully achieving its objective, and the objective is the same, that it is basically separating these two sets of data into two different categories. So you see that we can have multiple lines, or we can have multiple hyperplanes, and all those multiple hyperplanes, for example L1, L2 and L3, can successfully separate the two sets of data in two categories. So this point I have explained here, that we can have multiple hyperplanes L1, L2 and L3, and all these hyperplanes can be successfully achieving their desired objective. Okay, now let's try to understand these support vector machines through different scenarios, right? So I have added different scenarios in which we will have a variation in our data set, and we will see that how each scenario is being affected by different support vector machines, right? So let's see that the scenario number one is to identify the right hyperplane. So we want to identify that which hyperplane is the right hyperplane which is solving my problem. Here in this figure you can see that we have three different hyperplanes which are A, B and C. Now we want to identify the right hyperplane to classify star and circle, because we have two different sets of data here. We have some stars here, we have some circles here, and I want to have a hyperplane which can basically successfully classify these two sets of data. So you can see that this hyperplane A is not basically separating the two sets of data, right? Similarly, this hyperplane C is also not able to successfully classify the two sets of data. But if you look at this B line, this is basically providing me the correct classification, because it can distinguish between two sets of data, and it can classify this set on one side and this side on other side of the plane. So you need to remember a thumb of rule to identify the right hyperplane. So we need to select the hyperplane which segregates the two classes better, right? So I will say that this is my right hyperplane if it segregates the two sets of classes. In this scenario, of course, you will see that the hyperplane B is able to perform its job successfully. Now let's consider scenario number two, in which we want to identify the right hyperplane. Now here we have three hyperplanes again. We have A, B and C, and a, a little bit different thing is that in this case all these three hyperplanes can be are able to achieve their desired objective, right? So all these hyperplanes A, B, and C can segregate the classes very well. So how can we now say that which hyperplane is the best hyperplane for this problem? Because all these hyperplanes are basically performing well in segregating the two classes. But we need to select one hyperplane or one line which is the best among these three. So what is the criteria upon which I can decide that this hyperplane is the best one? Now here, maximizing the distances between nearest data point, either class, and hyperplane will help us to decide the right hyperplane. So here we are establishing a rule, and the rule is that we want to maximize the distances between nearest data points and the hyperplane. And what are those distances? For example, you can say we have one class here, we have one class here, and we have a distance of this instance to this hyperplane. Similarly, we have a distance of this point or instance to this hyperplane, and we have a distance of this instance to this hyperplane, right? So we have different distances of different instances to each hyperplane, and the rule is to maximize the distance between the nearest data point, right? The nearest data point means the data point which is close to a hyperplane on either class, and the hyperplane will help us to decide the right hyperplane. So we can on the basis of the distance of the instance from the hyperplane, we can decide the right hyperplane. And this distance, the distance between the instance or the data point to the hyperplane, is known as margin, as I explained before. So now this phenomena will be further clear to you in the next figure, but right now we have two scenarios and we have seen two things in our scenarios. If we have multiple planes, those multiple planes might not be classifying the input data set correctly. So that will be scenario one. Or there can also be a case that all those lines or hyperplanes can be classifying the data points successfully, and then we need to choose the best hyperplane between those multiple hyperplanes. Okay, so in this figure you can see the distance or margin thing, which I also explained in the previous slide. You can see that this black line here, this black line here, and this black line here is basically the margin or the distance of a data point from the hyperplane. So this data point have this much distance from this hyperplane, this data point has this much distance from this hyperplane, or the same data point, this one, have this much distance or margin from this hyperplane, which is C, right? So we have different distances or margins of each instances to different hyperplanes. So above you can see that the margin for hyperplane C, which is this one, is high as compared to both A and B, right? So if I compare the margin of this data point to A or to C, so I can conclude that the margin of this data point from A is low, but the margin of this data point to C is high, right? So we name the hyperplane as C. So we can say that since the margin of these different data points are higher with C, because we need to see both of these classes, and we need to see that for both of these classes which hyperplane has a maximum margin. So in this case we can see that this hyperplane C has the maximum margin for both of these two classes. So we can say here that the right hyperplane or the hyperplane which we can select is C. Another lightning reason for selecting the hyperplane with higher margin is robustness, right? Because remember the very first slide which I showed you, the very first figure, is that if I don't have this maximum margin thing, then my algorithm or my solution will not be robust, or with addition of new data points I can have misclassifications. So if this margin is maximum, then the rate of misclassification will be low. If we select a hyperplane having low margin, then there is a high chance of misclassification. So if the margin is low, then the chance that the classes or instances will be misclassified will be higher.